Maybe I'll write it on the pad. If you want to write examples of how to do unit conversion appropriately, and one of your steps that you have in your calculations has this in it, then you've shown metric conversions on your note card, and I take it away. So please don't let me take your note card away. It's a study tool, really, is the biggest part before you get there, but also it's a comfort thing when you're here. You can put anything you want, or you can put nothing. Some students don't bring note cards at all.
Wait, how big is the note card again? Because I'm going to probably cut it out of a piece of paper.
3 by 5 inches.
3 by 5.
Yep, it's in the syllabus too. In that giant document, you can do Control F and you can find lots of stuff in there.
I don't have any of those. I'm just going to print it and cut it.
Sorry, I can't hear. Can you say it one more time?
Once the test has been handed out, you write the metric conversion units from memory, like in the corner as a note on your test?
Yeah, you can write it on the test. You actually tear the periodic table off. So I give you a periodic table in the front of the exam. You can tear that off, and it has some conversion factors in the back, just not metric conversion factors. So I'll give you grams AMU. You can write anything you want on it. You can write anywhere you want on the exam. I would try to, the reason I'm asking you to memorize it is not to see how long you can cram it in your brain to write it down on paper, right? So sometimes it's a comfort thing, you just do want to have it written down as well, that's fine. I really urge you to actually commit it to memory, to be fluent in those conversions. Questions? Other questions about that? That's the only limitation on this note card. You can literally have anything else, but if you have anything that allows you to have a crutch so you don't have to memorize the metric system conversion units, then that is not allowed.
I noticed on your exam one, in the example for the general chemistry, you did state the AMU to grams conversion. Are you going to have that on our test?
So the activity that you were given before lab this week, or tonight, you'll be given, is a whole bunch of practice of conversion factors. You will receive a similar table at the bottom. The front page of that has the conversion factors. It has something like this, and it has additional conversion factors you would need. I'm not expecting you to memorize. If you need to know pounds to kilograms, I'm not going to expect you to memorize that. Grams to AMU is another one I'm not going to expect you to memorize. So hopefully you're using it enough that it's become second nature, but I will provide you with conversion factors that you need. I will not provide you with statements of what the number on the bottom of the periodic table is, or how to use these, but you will have them, so you'll have to know how to use them. That is the other thing. Okay? And then you will not be allowed to bring your own little periodic table card that I gave you because I provide one that's big. And I was told that on the activity from lab this week, the pre-activity, that periodic table was illegible. The one I give you on the exam will be very clear and easy to read, plus you'll have these on the walls. So you will have a periodic table. You cannot bring your own because you already have the 3.5 by 5 note card. And what was the other thing I said I was going to say?
Calculators?
Yeah, you can bring a calculator with you, any calculator you want, as long as it's not a smart device that's Wi-Fi enabled. If it has a periodic table built into it, use another calculator. Some of the new fancy ones do. That's just going to get you in trouble. If I happen to walk by and you have that pulled up, then that's going to be academic misconduct, and it's just a situation we don't want to get into. So let's not do that. So if you have one of these super fancy graphing calculators that's Wi-Fi enabled, that has a periodic table in it, I will bring some TI-84s. You can borrow one of those. I only have 30 of them, though, so there's not enough for everyone in the class, or maybe 25. But you're always welcome to borrow one. But I don't recommend using someone else's calculator for an exam, because a lot of this is about scientific notation. So if the first time you're using a calculator and trying to do scientific notation on a calculator is during an exam, you already have stress and anxiety, so let's just not add on top of that a brand new calculator. Does that work?
Yep.
So the calculators that I'm going to bring basically look like this. So if you forget yours, it's okay, I got you covered, but it's not ideal. All right, any other questions about exam 1? Are you all going to impress me? Are you going to show me how good you can do on this exam? I know a lot of times students feel like it's an adversarial thing, but I really want to see you succeed on this exam. So as you're studying, use me as a resource. I have office hours before the exam again. Stop by my office if you need to. Post the Blackboard. I think I realized today that I'm not subscribed to one of the Blackboard discussion forums, so I will get onto that as well. I don't know, 30 to 40-ish. The old exam that's posted up there is probably similar in length. But it's hard to say because in the short answer section, the questions are A through D because it's multiple parts about the same topic. So I don't really have a number. Jay?
Is it the whole class period we have to take the exam? Or
Say again?
is it the entire class period?
Yep, we have the whole class period, which kills me. I love the long class periods because we get to work through problems. I hate that it takes up 3 entire class periods to do exams. University of Delaware, we used to have out-of-class exams on Saturday mornings.
Oh, no.
You say that, but students actually loved it because then you didn't have any other, they didn't have any other classes to worry about at that time, and it did allow for some freedom. I know that we can't do that here. People have families, which my student population did not there. There's a lot of other complications, but it's just a different way of doing things. Okay.
Your students have families?
They didn't have kids. They were more traditional age students, and so I didn't have many students that I was aware of that had their own children and familial responsibilities. Okay, so we're going to spend the first 15 minutes at most working 2 problems. These problems are indicative of what will be on the exam. I have 2 problems almost very similar to what you're going to see here on the exam. This is Chem Activity 2. We didn't finish it in class, but there's a lot of these types of questions towards the end. So if you want to practice, if you don't feel confident, go back through this. Hopefully you saw my announcements too about the dynamic study modules. There's a lot on the basic math side, unit conversion, scientific notation, significant figures. There's some on the basics of an atom and unit conversion on that side as well. So use those resources and study up. All right, so if you have not already, please go ahead and write out the process. Remember, we're focusing here on dimensional analysis. The questions like this that I have in the exam are in short answer. It is not about the answer that you give. It's about the process you set up, and then some small portion of the credit will be given for the actual answer. You do need to know how to use your calculator, and you should be able to get an answer and be like, this is reasonable or not. So go ahead and make sure you have this written out, and then we'll talk through the process here in a minute. And then the second question you have written down. If you're already done with the first one, you can work on the second one. Do you have the worksheet for today? Not written at the top. If you're stuck, ask the people around you or flag one of us down.
Well, you take the percentage out of it. Because you make the percentage out of the percentage.
Make sure you write that out super clear.
Just the percent. You have to make that to That's the word like multiply plus multiply.
Weight of
The same scenario.
No, flip where they're placed. Yes, the whole comparison line of alpha flip where they're placed. That way you're going from atoms. Other than that, you have a circular.
Okay, so wait, flip, put this over here and this over here?
Yes.
Oh, okay.
That's the only thing I would do. You don't have to change it though. You're right. I wouldn't change it. But yes.
Okay, and then just
Yes.
And then I changed it to 3 right here.
All right. When we're working through this kind of a problem, how do we make sure we don't get stuck in all of the data that we have?
We're supposed to write at the beginning.
Read the problem. Once you read the problem, what do we take out of it? What's the most important parts?
But you start with
I'd be careful. So when you say numbers, sometimes I'll have additional numbers in a problem, or you'll see additional numbers. So it's not just about the number. It's about saying, what is the question asking us? So in this case, what are we starting with? What's our starting quantity? Morgan?
8.567 times 10 to the 24 and 29 SI.
Be a little bit more specific. Someone help out?
Atoms, yeah, sorry.
So it's this many atoms of silicon-29. And what is the question asking? In simpler terms. Even simpler than how many grams. How much does it weigh? So it's saying we have this quantity, we have this amount of them, and then the question is, well, how heavy is it if we have that many of them? So then on the far right side here, we're going to say equals, I don't know, grams. Some amount of grams. And then when you think about, well, what conversion factors do we have that allow us to go from how many to how heavy in that specific set of units? So what conversion factors might we want to start using? Can I have some volunteers? Okay, so if we use, what do you mean the mass and AMU? Can you be more specific?
The 29 silicon, 28, 29, 765 AMU over 1 atoms, 29 silicon.
What does that conversion factor allow us to do? Okay, so mathematically allows us to cross things out. But what is it doing? What are we doing with that conversion factor? If we're unable to say that in a sentence, then we're probably just like in math brain and not thinking about what are we actually doing? Shelby? Great, we're going from how many to how heavy using the weight of AMU. So we did what we asked for, right? We went from how many to how heavy. We're done. Almost. So then we want to say, well, we know the weight in AMU, but we need the weight in grams. So is there a conversion factor that allows us to go from the weight in AMU to the weight in grams?
Would it be the 1.606 times 10 to the 24? Or no?
We good?
Negative.
Okay, because this statement is 1 AMU is a lot of grams. And it's not. It's a very small fraction of a gram. 10 to the negative 24th AMU. Okay? And then we go back and we say mathematically, we converted from atoms of silicon to the weight in AMU, the weight in AMU, to the weight in grams. And then we can calculate that mass. Does anyone have a value they want to share that they feel like is appropriate? Tay?
412.2.
Did anyone else get that value? Do we feel like that's an appropriate number? How do we check? How do we check to make sure that's a realistic value? So sig figs we can focus on as well. But I want to know, should the number be a really big number? Should it be a really small number? Should it be close to 1 or 10? Because remember, we're dealing with numbers that are insanely small and insanely big. Like, it's hard to wrap your head around 10 to the 24th. Because that is literally a billion, billion, million.
Where did you get the negative from? Where did you put it?
So this conversion factor is one that I will give you on an exam. And it is 1 AMU is equal to a very, very, very small fraction of a gram. Specifically that exact fraction of a gram. So that's one thing I left out on this problem, and I should have given that to you. So mathematically, if we're comfortable working with scientific notation, which if you're not, that dynamic study module is a place to go practice. What I want you to think about is we have times 10 to the 24th and 10 to the negative 24th. We have those two values, one on each side. What happens when you multiply those two things by each other? Cancel out and give you 1. So that means that our answer shouldn't be extremely large or extremely small. Our answer should be somewhere around 1,000 to 1,000th, somewhere in that range. Right? That's a pretty narrow window compared to a billion, billion, millionth. It's a lot closer. So then we say, okay, those two cancel out, and then on the top we have 8 times 29-ish times 1.5. So that should give us a value that's, I don't know, 100, 200, 400. That seems reasonable. You should always be thinking about how big is a number. What power of 10 should it be raised to? And so doing mental math with the scientific notation is a way to get you there. Questions? Want to do the second one? All right. I'm going to go ahead and see what the answers were. Go ahead and set this one up. Make sure to focus on that. What is our starting quantity? List that first. What unit are we trying to get to? Are we going from length, weight, mass? What are the different... What are we trying to convert to? Take about 3 minutes to set this up. Make sure you have it set up properly.
They can follow me first, and then and work it backwards.
I put in what I put in.
Thank you.
Michelle working on it.
I mean, I just took that one. There's this 27.
All right, we have exactly 12 responses thus far. Does this bode well for the exam on Wednesday?
I'm just really slow.
Okay, but you all have the process down, right?
It's hard to put it in this.
It's just taking.
So use your friend E. E means times 10 to the.
I have it.
So I'd like to hear from a new voice. Someone who has not yet talked today. Let's bring it back together. Okay. When we look at those two bookends, what are we starting with? What's the quantity we're starting with? I saw a lot of people either getting lazy on this or just not really identifying what the starting quantity was. So, what do you have? Alright, so you said 32.6 grams. So we have a unit, and it's of silicon. Did anyone here just write 32.6 and just go on with your calculations? Yeah, a couple people. I saw that. Alright. We'll see in a second why that's a really, really bad issue that you're going to run into. So, then we go to the next step. We say, okay, we know how heavy our silicon is. What are we trying to find? What are we trying to figure out? How many of them we have in atoms. So on the far right side, we're going to say equals, question mark, atoms of Si. Okay. What conversion factor do we use first to help us get from how heavy to how many? Sorry. 1.6606 on the bottom. 1.6606 times 10 to the negative 24th grams. What did that allow you to do? Okay, so we stayed in weight. We're still talking about how heavy it is, but we went, instead of talking about grams, we're now talking about AMU. Why was that useful? Sorry, I couldn't hear you. Because the conversion factors we have to go from how heavy to how many are an AMU per atom. So, fair. So then what conversion factor did you use next to go from how heavy an AMU to how many? Where'd you get that number? Why are you pointing over there at the wall? Why? Okay. So this is where most people get hung up on this type of a problem. Is they say, well, I got to pick one of these three isotopes, right? Which one do I pick? But if we don't specify, then we're saying, well, what is the abundance in nature? We can either calculate the average isotopic abundance based off of the 92%, the 4%, or the 3%, or we could just use a number in the bottom of the periodic table because that's already been calculated for us. So if we're assuming this is on Earth and we're not specifying it's anywhere else, then you can use the number in the bottom periodic table, and that is the average mass in AMU of one atom. But what could she add on to be a little more accurate here? Is it any atom?
No, it's one. This special atom.
All right. So that last part is really important. And so what I saw a lot of people do over here was 32.6 grams and forget out of silicon. But then by the time you get over here, you're not paying attention to what atom it was, and you're like, oh, I'm just going to pick, like this will work, right? This gets me from AMU to the number of atoms, so that's fine. So specifying what it is we're working with at every step of the way, that this is silicon. It's not silicon 27, 28, or 29. It's all of the naturally occurring silicon in the relative abundance that they exist in the world. So we'd have to go through and specify which one it was. If we're not specifying one of these, then we use the number in the periodic table. Otherwise, it looks beautiful. So how many atoms did you find? Thank you for showcasing what you do not want to do in the exam. Okay. If we eyeball this, what are we thinking? Is this going to be a big number or a small number? Talk to your neighbor. Is this going to be a really big number? Greater than something? Pick a number that's greater than. Or is it going to be a really small number? All right, let's do this thumb vote. So we're going to say thumb sideways, up versus down. Thumb sideways is about 1. Thumb up is going to be greater than 1. Thumb down is going to be less than 1, like a really small fraction or a negative number. What do you think this number is going to be? Greater than 1, around 1, or it's a lot smaller than 1? Why? I guarantee you a lot of people plug this in their calculator and they get a number that's smaller than 1. It's going to be 10 to the negative 22nd or something. Why is that not okay? How many students are in this class? If I did some fancy-ass math and I came up with 10 to the negative third students, what's wrong with that?
There's no students. There's less than no students.
It's the fraction of a student. We can't have a fraction of a student. Students come in whole integer quantities, right? It's either 1 or 6 or 12 or 2,000. So you always have to think about what's a reasonable answer to this. Dividing by an exponent can be a little tricky, so make sure you're comfortable with that. I always suggest putting parentheses when you're putting things in your calculator. So if you're not comfortable with the exponents, put parentheses around it so you get a number. But is it going to be big or small? How big?
Not as big as the first one.
10 to the negative 24th on the bottom is the same as 10 to the 24th on the top. So I know this number is going to be about 10 to the 24th. Maybe a little bit bigger or smaller than that. Can someone say the number they have? Share that. Shelby?
6.99.
Sounds like in the right ballpark. So if I got that number, I'd be okay with it. I wouldn't necessarily go back and check my math. If I got 10 to the negative 23rd, I'd be like, something went wrong. I need to go check my calculator. 10 to the 25th. I don't have my calculator in front of me.
Is that 23rd? What's that saying?
So those two are going to be about the same. That's going to be 10 to the 20. So I would go back and check your math. Is anyone super confident in their calculator skills and have the actual value?
6.98.
Times 10 to the
23rd.
23rd. All right. Raise your hand if you have 10 to the 23rd and you're confident in your skills. If you have 10 to the 25th, raise your hand. Okay. So just a matter of going back and looking through. That's by crowdsourcing. I'm not going to say it's 100% accurate, but on your denominator, yeah. So we can just meet briefly after class and look at how you put it in, or ask the people around you who might have got the right answer and see what you might have done as a mistake in your calculator. So on the exam, for instance, if you got 10 to the 25th instead of 10 to the 23rd, you'd probably get, 4 points out of 5 on that question. If you got 10 to the negative 23rd, then it shows that you didn't think about whether that was the logical answer or not, and that would be worth maybe 2 points out of 5. So I'm not super worried about the calculator as long as your answer could make sense. Does that seem reasonable? So there will be some judgment on my part, whether I can see that your answer shows that you at least had some grasp of what the answer should be. If you get an answer that's totally messed up, like 10 to the negative 23rd, if you write a little note beside it and like, I know this should be greater than 1, but I ran out of time, then I'll actually give you more credit. If you can acknowledge when you made a calculation error, but you can't identify it in time, then that's better than not identifying it. Courtney?
Will you sign off if we just put, like in this case, 32.6 grams and not kilograms?
Yes. You have to specify whether it's a specific isotope, whether it's a overall weighted average. Yes. The first exam is critical that you show all of your work, that you show exactly how you set it up and how you work through a problem. Okay. Does this give you an idea of what to expect on the exam? I'm not going to throw any curveballs around this topic. You need to be able to do this forwards and backwards for isotopes and for weighted averages. And if you can do this, then you can probably do a lot of the other unit conversion questions that I'll have for you. Cassandra, you have a question? Okay. Cool. So that was our intro that had nothing to do with our learning objectives for today. So this class, like all chemistry classes, does not slow down for an exam. Exams happen. They are a necessary means to make sure that you keep up with what you're supposed to be doing throughout the semester. But lab this week, starting tomorrow, is on molecular shape.
What?
Molecules.
Oh.
Right? Have we talked about molecules at all in this class?
We watched the video.
Okay, so there's a pre-lab that has some stuff in videos. But in this class, we haven't touched on it yet. So the rest of the class today will not be on exam 1, but it's try to get you up to speed so you can hit the ground running with your lab this week. Okay? So make a little bit of room in your brains for some new material that's going to be really valuable when you go in the lab this week.
So the pre-quiz for today.
Pre-quiz for today was valid because that was the electron configuration. Okay, so the first 2 slides are part of the exam, and I'll say when that's up. But once we get into molecules, we're beyond that. So this is basically what was on the pre-class quiz, and this is what will be on the exam. Determine the number of bonds each atom can make based on the group number. This also means you can determine the number of valence electrons. But beyond that, and related to the quantum description. So you need to be able to write the quantum electron configuration, and then use that to say how many valence electrons there are, and hence how many bonds the atom might make. But you're not going to have to draw a Lewis structure. You're not going to have to determine the steric number in AXE group. That is for your lab, not for the exam. It's for exam 2. All right, so we're going to do a few quicker questions. We're going to do these relatively quick, because hopefully the pre-class quiz got you set up for this. So the question is, how many bonds could an element in this family make? So the family is, it's called the carbon family. That's what the Lewis dot structure looks like for it. So talk to your neighbor if you need to, but I'm going to give you about 30 seconds to click in your response. How many bonds would an element in that family make? Couple more seconds. Got 38 responses in. All right, closing out. What group number is this we're talking about? Group number 4. And everything in that group is going to make 4 bonds. What about everything in what's called the chalcogens, which is oxygen, sulfur, selenium, tellurium? Go ahead and click in your response for that one. A couple more seconds. All right, closing out. All right, would anyone like to explain which answer they chose and why? I'm showing the responses for everyone. Okay?
I said 6 because it's in group 6.
Okay. So how does that relate to the number of bonds that it can make? Courtney?
It only has 2 open slots.
2 open slots. What do you mean?
Well, because the open is 2, and the next one is 6. So there's 2 missing to make it.
So we briefly mentioned the octet rule last class. The octet rule is that all atoms strive to have their outer group of electrons, the valence electrons, look like the noble gases. How many electrons do the noble gases have? How many valence electrons do they have? So in order to become like a noble gas electron configuration, they need to have 2 electrons shared with them. Each one of those is going to be creating a bond. So it's always fun when the majority of the students in the class are wrong.
Wait a minute.
I got it right.
But I thought you were agreeing with us. Wait a minute.
I never said I agreed.
Wait.
And I appreciate that Courtney pulled that answer out. All right? So let's talk about the nitrogens. Things that are in the column the nitrogen is. Think about what group it's in, how many covalent bonds that group typically makes. Talk to your neighbor, try to figure it out.
I thought you were agreeing with the thoughts going, like, do you have to know specific parts?
That's a good question. Ask that when we start talking about the whole class. All right, a couple more seconds. Closing out. Can I get another volunteer to share what they answered for how many covalent bonds something in the nitrogen group would make? Why 3? Was it Ryan? Sorry, I heard a voice from over here. It has 3 available places for electrons to go. So it doesn't have bonds yet, but the idea is that if 3 other atoms came in, then it could make 3 individual bonds to get to its total of 8 electrons. Does that mean that it steals those electrons? Possibly. It could, right? If nitrogen stole electrons, it would be N3 minus, as is drawn right there. But the idea is that if it has another element that comes with its own electron, right? Hydrogen has 1 valence electron, that makes a bond.
They merge.
There's another hydrogen that brought one electron, and another that brought one electron. And so that could make 1, 2, 3 bonds. Could oxygen make 3 bonds with hydrogen? It could only make 2 if it really wanted to, right? One there, H2O. That's why water is H2O, not H3O. What about carbon? Just happened to be that number was the same either way you look at it, how many electrons it has, versus how many it needs to share in order to get to its full octet. I think, do we have one more? I think we have the halogens as well. So halogens, how many bonds can they make? Go ahead and click in your response. Couple more seconds. And while we're waiting for the last couple clicks, what group are we talking about here? Group number 7, we call them the halogens. In order to get to that octet configuration, we only need one more electron here to bond. So if it stole that electron from somewhere, then it's going to be a -1 charge. But it can also share it. And so that's a property that we're going to be talking about starting next week, is whether 2 atoms are likely to share electrons or whether likely one is to steal it and rip it away from the other one. So that's based off a property called electronegativity, which might actually be in your pre-lab quiz.
What?
But I'm going to try to see if I can weight that question to be worth nothing, or very little. There's a question in the pre-class quiz for those people who have pre-lab quiz that I think is like what we should be able to do at the end of 2 weeks from now. So I'm going to try to modify that so it doesn't have any weight. Okay, so this is kind of the end of tying together what you should be able to do by exam 1. So you should be able to look at a periodic table and say, how many valence electrons does any element have in the main groups? You notice that we're not focusing on the transition metals, right? We're looking at the main group 1, 2, and 3 through 8. We're kind of ignoring that middle section right there. That group has different properties as a transition metal, and so we're not going to be focusing on that as much because, honestly, most of biology doesn't focus on it as much. Courtney, do you want to add something?
I think I should wait, because I think it might have to do with what you said we're learning in 2 weeks from now. So
About polarity or about those things?
yes. Just because salt is made from ionic bond, do they, this is probably a dumb question, is there a way to see just from like the chemical, like, thing?
That's a really good question, actually.
Does that make sense?
So maybe we should just touch on that now because it kind of is part of the discussion we've had up until this point. So this property of atoms called electronegativity, if we're over here on the far right side, those atoms are pretty close to an energetically stable configuration, right? The noble gases are stable. So they're just a little bit away. So if they could just pull an electron away from something else, they would be much more stable. So we say that they have a pretty big pull on electrons if they end up interacting with another atom that has an electron. But if you put 2 of them close together, both of them have a strong pull, it's going to be equally shared between the 2. But if you put together like a fluorine and a potassium, does the potassium have a really strong pull on its electrons? It's actually fairly stable if it loses that electron. And so these are said to have very low electronegativity. So if you pair together something on the far left with something on the far right, you're going to make an ionic bond. You're actually going to transfer the electron from the one that can give up electrons to become an ion, positive ion, to the ones that will gain the electron to be like noble gas. So you'll have a negative ion on this side, positive ion on that side, and the 2 converge together, and there'll be a salt, and they're not sharing that electron at all. The one on the far right pulled it away from the other one. So that kind of gets you in the mindset of salts, and that's the whole discussion of salts. So there will be, the week after this, our lab will be about chemical reactions and about how we name salts. So that's a topic we'll get into. All of these descriptions come from the valence electrons. Valence electrons, remember, are the s and the p electrons. You can see that here. That for group 6, it's how many, let's say, 2s and 2p electrons it has. That's how many valence electrons. It's only about the s and p electrons. So there's 2s and 5p electrons here, 2 and 6. So when we're talking about valence electrons, we're not talking about how many d electrons we have. We're only talking about the highest filled s and p. So hopefully you can kind of go back and forth between those. If you look at the periodic table, you're like, I know it's in group 5, it has 5 valence electrons. So that means 5 valence electrons, it has to have 2s electrons and 3p. Kind of some trends you're going to be working with. So that's where we wrap up with exam 1 material. And then we say, all these individual atoms, how do they all fit together? So I'm going to dive back to this real quick. Do we remember this animation from one of the earlier days?
Yeah.
So up until this point, we've been looking at this scale. Right, we've been looking at individual atoms, what's the property, what makes them up. The only reason that we've spent a month of the class talking about what makes up atoms is to then say, well, how do they interact with each other? So what we're going to do today is we're going to take that step back and we're going to say, okay, we're going to now go out to this level. I want us thinking about sugar molecule is composed of hydrogens, oxygens, and carbons. Now we know what those components are, what that means. Now we're going to think about how they interact with each other and how to predict what they're going to look like in 3 dimensions. You've probably seen in your biology classes videos like this. Does anyone know what we're looking at here? Phospholipid bilayer. So you usually see it as this kind of cartoony, like spaghetti between. But what I want to start us thinking about is that you can come at it from either side. That you can either look at it from the cartoony kind of side here, or you can look at each one of these dots. This is DNA, double-stranded DNA. Each one of these dots is an atom. So we're going to be saying, why are the atoms in that shape? Why do they arrange in a coil? And that's based off the properties that each one has and the 3-dimensional shape. So the lab this week that you're looking at is trying to think about when atoms do bond with each other, what shape do they have? And it's dictated by steric number AXC designation, which we'll be getting into here in a minute. So let's talk about Lewis structures. We're going to have you draw your own Lewis dot structure of CO2. You might have seen this before, and that's fine, but I want us to kind of walk through it. Here's some of the rules that we need. You have these written down on your paper. Under question, or right above question number, before question 4, these are written down. Here's an example. So I want you to look at these rules, look at how HCl is drawn. That's a Lewis dot structure. And I want you to try to draw CO2 as a Lewis dot structure. If you don't know where to start, ask those around you. I'm going to give us about 3 or 4 minutes to try to follow these rules, so you have to figure a couple things out, and then figure out how to lay everything down on a piece of paper. So maybe it's worth kind of debriefing how we got this Lewis dot structure for HCl. How many valence, if we follow these rules, how many of these valence electrons came from hydrogen? So I'm going to draw that in red. I'm going to color that in. And how many valence electrons does chlorine have? So chlorine's a halogen. It's in group 7. Has 7 valence electrons. Okay. So the ones that I drew in blue came from chlorine. The ones I drew in from red came from hydrogen. We're not 100% sure which of the two came from hydrogen and which came from chlorine, so don't get too worried about that. Electrons must be placed in pairs. Looks good. I saw a couple people place individual electrons. So if you have 2 extra electrons, don't put them here. Put them together. So don't have any individual electrons for now. And then we have to decide the electrons have to be one of the two. They either have to be bonding, which means between the 2 atoms, and that means that a bonding is a pair. So 2 electrons makes 1 bond between 2 atoms. So up here in HCl, how many bonds do we have? There's 1 bond because there's 1 pair of electrons between the 2 atoms. And then how many lone pairs do we have? Lone pairs are pairs that are just around the atom. We have 3. A pair on the top, a pair on the right, and a pair on the bottom. Those are only around chlorine. Those are not bonded between chlorine and any other atom. They belong only to that one atom. Okay? So then how does CO2 fit into that scheme? So I saw some people drawing CO, and it doesn't matter where we put them for right now, but the lab this week is all about where those should end up in space. So how many total electrons should we have here? Is 4 electrons good? So we have to think about that first step is make sure that all of the valence electrons are accounted for. Carbon has how many valence electrons? 4. How many does each oxygen have? So 4 plus 6 plus 6. So that means we have a total of 16 electrons. I thought you were pointing just at oxygen. I just said make sure.
Down for a reason. You have me second guessing myself.
Okay. So we account for all the valence electrons from each individual atom. And just to make sure, if we're writing CO2, that 2 means that we have 2 oxygens in that one molecule with every 1 carbon. So then we say, where do we put them? We either have to put them between the atoms, or we have to put them around the atoms as pairs. So I saw some people, let's just go ahead and put some around. How does that look?
Well, there's not enough around carbon.
We'll get there in a second. It's a good starting, it's a very good observation though. Did I follow the first rule? Did I use all of our electrons, all our valence electrons? Yep. We used all 16 electrons. Are they all in pairs? Yes, they're all in pairs. Are they either bonding or lone pairs? Bonding, lone, 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 bonding, lone, lone, lone. Okay? So according to those set of rules, we're good. But what's one of the major things that we just talked about a second ago of why atoms bond that I didn't think about at all here? Is that you, Olivia?
What?
I heard a term I really like. Stability. What do they have to do? What are they trying to, what is a way in which atoms can achieve greater stability? What electron count do they want around them? An octet. Okay? Is that true for the oxygens right now? Do they have 8 electrons around them? Yes. Does the carbon? Okay? So somehow we have to figure out how do we make these electrons count for both the oxygen and the carbon so that both of them can get that benefit, that added benefit. So what can I do? Can I change anything? What can I change?
more oxygen can share 2 on each side.
So I'm going to go ahead and move one of those lone pairs on the outside of oxygen to now be bonding. Okay, does oxygen still have that octet around it? These are in a bond that counts, both of them get to count what's bonded for that octet. So we have 2 lone pairs, that's 4, and we have 4 bonding. So this oxygen on the right still obeys the octet rule. We're good. Is the carbon there? What do we need to do to the carbon? Go ahead and move those 2 from the outside into the middle. And now we have an octet for every 3 of the atoms. This is the proper Lewis structure for carbon dioxide. So we have to make sure to do the things that were in those rules, but in addition, we have to try to get every atom to obey the octet rule. And what that means is sometimes moving electrons around. So, Monica?
I followed everything except how we got the second 6 up there.
Second 6. Oh, one carbon atom has 4 valence electrons. And then we have 2 oxygen atoms that each have 6 valence electrons. So every single atom in the entire molecule brings some electrons to play. And so all those have to be used in the final. Okay?
So bonds between atoms seem to be represented by the 4 electrons?
Yep, so there are, how many bonds are there between the carbon and oxygen on the left? There are 2 bonds because every bond is 2 electrons. So we can also, this is called the Lewis dot structure because they're all dots. We can also do a Lewis line structure, which lone pairs still look the same, but every line represents 2 electrons. But if we had started here, it might have been a little bit more difficult to move electrons around the way we did. So I wanted to start us off with the dots so we can figure out where all those electrons are.
Can you have a single bond?
You can absolutely have a single bond, but in this case, if we had just a single bond on either of the sides, because there's only 2 things it's bonded to, that wouldn't work. So methane, for example, CH4. Which ends up looking like so we have, around carbon, do we have an octet? We have 4 bonds, each with 2 electrons, that's an octet. Do the hydrogens have an octet, or should they? If hydrogen has a noble gas electron configuration, what noble gases configuration of electrons does it have? Helium. Helium has how many electrons? 2. So hydrogen is the exception to the octet rule because, well, there's other exceptions. But for the most part, we're going to be focusing on hydrogen is the only one that only needs to get to 2 electrons, and then it has a noble gas electron configuration. So on this process, it helps illustrate the process that I want you to go through and the steps I want you to think about. Wouldn't it be really nice if there's like a simple equation that kind of did it for us?
Yeah.
So there is. There's a nice equation, but I always hate leading with equations. What I want you to think about is there were 16 total electrons to distribute throughout this molecule. But all of these atoms needed to have full octets. So if each atom just had a full octet, what's the total number of electrons that we would have had to have in that molecule? So if we had had 8 electrons, 8 electrons, and 8 electrons, how many would that have been? 24 electrons is what we would have needed. So somehow we have to figure out how to make those 16 look like 24. How do we do that? How did we do that? Talk to your neighbor. How did we get those 16 electrons to fulfill the octet rule for all 3, look like the 24 electrons according to each individual atom's perspective, but we didn't have 24 electrons, we only had 16. How did we do that? All right, can I have a volunteer to share out for the group? I heard some good whispering. Caitlin, do you want to share what your group discussed? I saw little air quotes. That could be good. Not quite sure where you're going with that. Someone else want to chime in? How did we get 16 to look like 24? There's still only 16 electrons here, right? But we fulfilled the octet rule for all three. How did we do that? Carmen?
Created double bonds.
Okay, how did that help?
It helped with the octet rule.
Okay, Monica?
Are they sharing electrons?
So if it is only by itself, it only counts for itself. But if we share it, each electron that gets shared gets to be counted twice. Once for each atom. From each atom's perspective, if I'm sitting here in the middle on carbon, I'm like, oh, it's cool, I got 4 on that side, I got 4 on that side, we're good. But if I'm over here as oxygen, I get to see those 4, and I get to still count those as my own. So what we need to think about is, how do we get those 16 electrons to count? How many of those need to be counted twice? Maybe that's the way to say it. 8 of them need to be counted twice, right? What do you notice about the difference between these two numbers? 8. So there's this equation that basically calculates that for you. It's the total number of everything had an octet or duet, which we call n. And then we subtract from that how many we actually have, which we call h. And that's the number of shared electrons. But you can really do it without the equation. But we're going to call that n. We're going to call that h. So our equation is n minus h is the number of shared electrons. Okay? A lot of people think this is like some voodoo magic crap. It really is just saying that in order for electrons to look like they're more than they are, we have to share some of them. So let's take a look at using that. So our equation, number of shared electrons equals number of we'd have to have if we had octets for everything, minus how many we actually have. So I think there's a table, and we kind of already did this. So look a little bit down on that sheet. Fill in what S means, what N means, and H means, and then on the top of that next page, fill in that table for what those values are for each element, and we'll kind of walk through that. So this is not a clicker question. But for now, go ahead and answer questions 5 and 6. And then if you've got that table filled out, go ahead and start drawing out the other molecules.
Which one is the N? So this
What is the number you need and what is the number you have?
Okay. So the one you have is. So this would be 8, this would be 16. What? Oh.
You just wrote it somewhere else.
I did.
Okay.
I was like making notes. I didn't even realize it was on there. Just
If you haven't already, make sure to complete the table at the top and the back side. It should confirm what we've already done.
So there's 8.
Which is how many bonds? All right. let's go ahead and fill in this table. I want to do a couple practice ones before we leave class today. So in this table, if carbon had an octet, how many electrons would that be? It's 8 electrons for that octet. What about oxygens?
16.
We have 2, and every one has 8 electrons as an octet, so that's 16 in that box. What about valence electrons? How many electrons do we have for carbon? Carbon has 4 valence electrons. There's only one of them. Down here in the oxygens, how many valence electrons do we get from oxygen? That is 2 of them, and each has 6 valence electrons, so that's 12. So then at the bottom of our N column, how many total do we have? 24 electrons. How many do we actually have? 16. Those are the exact numbers we just looked at before. So this is kind of where it comes from. So if you find the difference between these two then, how many shared electrons should we have? So S equals 8, which means how many bonds do we have?
8
Divided by 2, because 2 electrons per bond equals 4 bonds. Okay, does that align with the structure that we drew? 1 oxygen on each side. And here's the last part. If we have 8 electrons that are shared, 8 out of our 16 electrons are shared, where are the rest of them? What do y'all think? If 16 electrons we have that we're placing around the molecule, only 8 of those are shared, how many do we have left? There's still 8 unaccounted for, so what do we do with those 8? What are the 2 types of pairs of electrons we can have? Bonding or lone? So those leftover 8, those are lone pairs. So then we go in the molecule and say, where can we add lone pairs? Well, we have 8 electrons, so that's 4 lone pairs. That's the structure that we drew. So in essence, this formula helps us get there quicker. If we're not sure how many bonds we have, this tells us right away. And then we can say, well, all the rest of the electrons that aren't in bonds, we're going to use those for lone pairs. And you just figure out where they go in the molecule so you have octets. Want to practice? I think this is going to... One more question before we move on. Which of these 2 structures should we have? Go ahead and click in your response. Think about the rules, whether they both obey the rules. All right, a couple more seconds. All right, we have an almost unanimous vote for A. Why? Symmetry, balance. Okay, yeah, that's nice. One of the things I want to try to have you thinking about is, technically, this can't exist. It obeys all the rules we talked about. But the unevenness of electrons is a little less than ideal. So for this class, there's really, really big level explanations for this. But for this class, what we're going to say is that whenever we look at an atom, look at what group it is, how many bonds should it usually have to reach that octet, and then try to set that up. So oxygen has 6 valence electrons, means it needs 2 bonds, 2 bonds. Here, 3 and 1, it's going to be a little less stable, a little less even. Okay? There's way more in-depth explanations if you want to come to office hours, but for this class, that's going to be it. So, I think this will be valuable for... A lot of people packing up. We've got 3 minutes. Just because Sarah's packing up, she's okay too. As long as she's very quiet. So how many domains of electrons do we have around that central carbon? Go ahead and click in a response. This is not super concerning. It's kind of a base point. Somewhere to start a discussion. A couple more seconds. So there is this term called the steric number. The steric number is how many domains of electrons are there around an atom. A domain is a group. A group can be lots of electrons or a few, as long as it's kind of like one bunch. What would then the steric number be around each of the oxygens in that left structure? Go ahead and click in your response. See the numbers as they roll in. 1, 4, or 3. Each set of bonds counts as their own. There's one set of 2 bonds, so that counts. But then each of the lone pairs also counts as their own. So the steric number around that central carbon is 2. The steric number around each oxygen is 3 because the lone pairs are separate. So there are 2 more Lewis structures you can practice on. I know that lab starts in a few minutes. We have 1 more minute in class. Do you want to try to go ahead and draw ammonia? Follow the steps we did before. How many valence electrons should you have? How many octet, if you had octets or duets for everything? And then go ahead and draw it out. And I'm not doing this as a clicker question. So if everything had a full duet or octet, how many electrons would we have? What's our N? So we have 8 electrons for nitrogen. How many electrons does hydrogen need to get a full octet or duet? 2. It only needs 2. So that's 8 for nitrogen, and then 3 only need 2 electrons. And then what about our have? How many actual valence electrons do we have? How many does each nitrogen bring? Nitrogen brings 7 valence electrons, is that right? 5. And each hydrogen? So basically we have 8 electrons to work with. Somehow we need to make it look like we have 14. So how many electrons need to be shared? We have 6 shared electrons. How many bonds is that? Okay. So then we go ahead and write our element in the middle. We have 3 hydrogens. We have 3 bonds. That kind of makes some sense. So we'll go ahead and write. I'm going to do it as lines, but you can do it as dots if you'd like. And then we're done, right? What did I forget about? So we only accounted for 6 of the 8 electrons. That means we have 2 more. Is there anything that doesn't have their octet or duet? So we need to make sure to put that lone pair of nitrogen to give it that full octet. Now we've accounted for all the valence electrons. Everything has a stable octet or duet, meaning hydrogen only has 2. So there's a couple more practice ones in there. What's the steric number around that nitrogen? It's the steric number 3. Each domain of electrons. We have 1, 2, 3 domains of bonded and 1 lone pair.
So I guess
Might have to be after everyone leaves because I think everyone's free to go. All right, I will see you all either at office hours. By the way, there is extra office hours on Tuesday, 12 to noon in the tutoring center that I think some of our TAs are running. Good luck studying. Post questions to Blackboard if you have them.